There was no reason to expect anything unusual. A body approaching the heliocentric boundary should have disturbed its surroundings. Ions should have shifted. Dust should have scattered into measurable gradients. Instruments should have registered the faint haze that most interstellar objects drag behind them. None of that happened. For 12 continuous days, wide-field sensors along the heliospheric margin tracked a static background. Nothing moved against the stellar reference grid. Nothing broke the uniform field. Even when Pan-STARRS arrays cycled through deep survey mode, the sky remained unchanged. A thin vector crossed the field. At first it looked like a calibration echo, a single linear event, colder than the frame average, drifting along a path with no fringe signature. The photometric profile held steady. No broadening, no coma, no reflective halo. Just a narrow, silent motion line. Then, on the following sweep, a brief flux dip appeared at the lower edge of the frame. It lasted fewer than 3 seconds of observational time. The signal dropped below baseline, then returned with perfect stability, as if the instruments registered an object passing through, but without the scattering a body should produce. On the next pass, the scatter curve locked into a flat profile, no dust response, no forward scatter broadening. A field that should have shifted remained unnaturally rigid. The frame should have brightened. The field should have scattered. The profile should have changed with solar angle. It did not. The Discovery team logged the object with a provisional designation, 3I Atlas, a body entering the solar system without any detectable dust, gas, or ablative trace. The expectation failed. Something moved through the heliocentric boundary without announcing its presence. The first confirmation came from the Pan-STARRS 1 array on Haleakala. The system swept across the field in near-infrared mode, capturing a sequence of high-clarity frames. The object persisted in each one, maintaining its narrow reflectance core. There was no diffusion at the edges, no energy spill into adjacent pixels. Pan-STARRS 2 provided the second confirmation. Using a different filter set, the telescope recorded identical characteristics. The object held its line, indifferent to the wavelength sequence. Photometric stability, measured as constant across 6 successive passes. A thin vector rotated through the frame. When cross-checked with the Canada-France-Hawaii telescope, the result was the same. No thermal plume, no particulate show, no signs of solar heating across the surface. A body moving inward, but leaving no measurable disturbance in its path. Most interstellar visitors, such as ʻOumuamua and Borisov, revealed themselves immediately. The first displayed non-gravitational acceleration and unusual tumbling reflectance. The second carried a clear cometary halo. 3I Atlas did neither. The approach remained quiet. Ground-based observatories ran synchronized sweeps. Automated detection software searched for any faint gradient around the object. Even the wide aperture arrays tuned for zodiacal dust interaction showed nothing. A narrow trace advanced against a field of unchanging stars. Then came the procedural check. Operators attempted a forced recalibration sweep across the incoming vector. Systems returned a null signature. No phase shift, no thermal rise, no dust echo. A body was present in the frame, but the diagnostic routine treated the region as statistically empty. Energy models predicted a measurable temperature rise as the object crossed the heliocentric threshold. The rise failed to materialize. 3I Atlas entered deeper survey range in complete isolation. A body in motion, leaving no detectable footprint across the environment it crossed. Once the trajectory cleared preliminary classification, the measurement phase intensified. The focus shifted from detection to understanding how an interstellar object could move through the solar system and leave almost no physical trace. Initial thermal readings showed a surface that neither warmed nor cooled at the expected rate. Solar input should have generated a shallow heating curve. Instead, the curve remained nearly flat. The radiative balance stayed steady as a sealed instrument case. A thin vector glided along the background field. Spectral scans from near-infrared to mid-infrared wavelengths suggested a surface with unusually low absorptivity. The signature resembled carbon-rich composites but lacked the fine-scale features associated with them. The reflectance remained too stable for a natural, volatile pore body at this distance from the Sun. Trajectory analysis revealed smooth, uninterrupted motion. No minor deviations from dust impacts. No micro-oscillations from surface jets. The path remained coherent over multiple observation windows. A movement as steady as a satellite drifting in deep calibration mode. Velocity showed no sign of acceleration beyond gravitational influence. Every derivative remained within expected ranges. Yet the lack of environmental interaction produced a second inconsistency. Something traveling at that velocity through the heliocentric boundary should have disturbed the local dust cloud. 3I Atlas passed through it without a measurable grain displacement. Reflectance patterns remained narrow and sharply bounded. When compared with ʻOumuamua, whose brightness changed by a factor tied to its tumbling shape, 3I Atlas displayed nearly no variation. The reflectance curve held a tight central peak, as if the object rotated around an axis that kept its surface orientation stable. Reflectance, consistent as a polished calibration target under fixed illumination. Wideband spectral analysis detected an unusual stability across the red and near-infrared ranges. The curve lacked the irregularities common to weathered interstellar surfaces. There were no hydration bands, no carbonaceous dips, just a clean, cold return signal. Mapping its drift relative to the solar wind showed a surprising profile. Particles streaming outward from the sun produced almost no detectable effect on the object's motion. Even a small body should have registered slight pressure changes. 3I Atlas did not, a stationary buoy resisting a steady tide. The drift profile became the second major contradiction. A body that small, traveling that fast, should display measurable deviation when solar wind conditions fluctuate. Its indifference remained unexplained. Every telescope that observed it reported extremely consistent photometric output. Brightness stayed within a narrow band even when solar angles shifted. A stable value held through each pass. A thin motion streak crossed the lower frame. When the James Webb Space Telescope, spelled once, then stated as JWST, turned its sensors toward the object, the data confirmed the earlier findings. Spectral behavior showed minimal absorption. Thermal maps remained flat. No surface gradients emerged. A surface as uniform as a metal plate inside a vacuum chamber. Thermal inertia readings challenged expectations even further. The surface resisted temperature shifts more strongly than similar-sized interstellar objects. Heat transfer appeared slow, uniform, and unusually balanced. This indicated a material composition with strong thermal capacity and minimal heterogeneity. Natural bodies rarely display this level of uniformity without evidence of past alteration or resurfacing. 3I Atlas offered neither. Across ultraviolet, visible, and infrared wavelengths, the spectral response remained remarkably smooth. There were no emission lines from gas release, no absorption dips from surface volatiles, no signs of space weathering microfeatures common to bodies that have drifted through interstellar radiation fields for extended periods. A wavelength curve as smooth as a calibrated lamp under vacuum testing. The path angled inward on a shallow approach vector. Threshold models reconstructed its incoming direction with significant precision. It passed near the solar apex region, but carried none of the expected microdust tail that usually accompanies bodies from that direction. No fragmentation, no outgassing, no surface shedding. 3I Atlas moved as if shielded against the normal processes that alter an interstellar body. Across all measurements, a pattern emerged. Low thermal signature, minimal photometric variation, no particulate disturbance, no volatile activity. The object crossed the inner solar system with an isolation that resisted explanation. With the primary data collected, researchers compared 3I Atlas against the two known interstellar visitors. ʻOumuamua displayed irregular reflectance and non-uniform acceleration. Borisov carried the clear signature of a comet, complete with coma and tail. 3I Atlas aligned with neither category. The first contradiction appeared at the heliocentric boundary. A body in motion produced no surrounding disturbance. The second contradiction emerged during measurement. Its drift profile showed an unusual indifference to solar wind pressure. The third contradiction came during compositional modeling. Material analysis suggested a surface with uniform spectral return and high thermal inertia. These properties should align with dense carbon composites, but the spectrum lacked their distinctive features. Alternatively, metallic surfaces can produce similar behavior, yet the reflectance pattern did not match known alloys or meteorite classes. This inconsistency created a new challenge. If the surface was carbon-rich, hydration features should appear at specific wavelengths. If the surface was metallic, mid-infrared features should broaden under solar heating. Neither outcome occurred. Then a sub-millimeter reflectance shift appeared during high-resolution sampling. The deviation was small, far below 1% of the curve, but consistent across multiple passes. It indicated a surface that returned light with unusual coherence, yet still did not resemble any known category of interstellar weathering. A thin vector slid across the measurement panel. The object also lacked signs of space weathering expected from prolonged interstellar travel. Natural bodies accumulate microfractures, irradiation scars, and mineral darkening. This surface showed none of those markers. Comparisons with ʻOumuamua highlighted the absence of rotation-driven brightness variation. Comparisons with Borisov underscored the lack of volatile release. Comparisons with smaller trans-Neptunian objects emphasized the insufficient dust interaction. 3I Atlas stood apart. Orbit reconstruction placed its origin beyond the local interstellar environment, yet its surface did not reflect that passage. Natural bodies rarely maintain such uniformity over extended timescales. The composition anomaly offered no straightforward resolution. What remained was a catalog of measurable inconsistencies. No dust halo at entry, no solar wind interaction, no compositional markers, no surface aging signatures, no detectable debris trail. All of it recorded, all of it empirical. 3I Atlas moved through the solar system in measurable silence. After perihelion passage, the object continued its motion along a stable outbound trajectory. The observational intensity reduced in stages as its brightness declined. No new data emerged during this phase. The object maintained its narrow reflectance core. No dust trail appeared behind it. No thermal shift registered as distance from the sun increased. A thin outbound line crossed the final observation frame. Wide-field surveys tracked the object as it retreated toward the heliopause. Brightness decreased with predictable attenuation. Every wavelength band showed the same gradual fade. The stability persisted to the final measurable moment. There was no change in rotation, no sudden fragmentation, no irregular acceleration. Just steady, silent motion outward. The solar wind interaction remained minimal, even at increasing distance. Trajectory models projected a clean exit path through the outer heliosphere. No environmental disturbance appeared along the route. Silence replaced tension. Data streams narrowed to a final sequence of diminishing points. The field grew uniform again. The object reduced to a faint trace, then to a dim fragment of motion, then to nothing measurable. 3I Atlas crossed the boundary in the same way it entered it. Quiet, unaffected, empirical to the last frame. That is 3I Atlas. Radiant, empirical, still.